Hello everyone. First, let me introduce myself. My name is Štajduhar. I am a computer scientist specialized in machine learning research. I am presently affiliated to the University of Rijeka Faculty of Engineering and the Center for Artificial Intelligence and Cybersecurity in Rijeka. Today, I will be discussing the perceived purpose and usability of AI. In the first part of the talk, I will be discussing what is AI, how it was portrayed in the past, and how it's perceived nowadays. Next, I'll try to formalize an abstraction of a typical AI setup. Finally, we'll be going over some examples of contemporary AI applications. I hope you will enjoy the talk. Before explaining what AI is today, let us first discuss how it was perceived in the past. Creating machines that think and act like human beings has puzzled scholars from the dawn of time. While pondering on this concept, ancient Greek philosophers have established the rules that govern correct thought, consequently laying out the foundation for contemporary theorem provers and deduction systems. The generally accepted idea, originating from that time, was that computation could be used to mimic reasoning, which in turn would lead to understanding the processes influencing behavioral patterns. It turned out, however, that it is difficult to encode rational thought. Furthermore, the range of possible problems that can be solved using this technology is, unfortunately, rather limited. More recently, researchers shifted their attention towards laying out the foundation for building machines that think like people. Trying to mimic the wider thought processes going on in our brains, rather than focusing only on the rational part, led us to the cognitive revolution in the 60s. The idea of information processing was then substituted by the dominant behavioralism in psychology. But were we able to exploit these findings for advancing AI? Well, we did get the inspiration for the one-learning algorithm hypothesis, which basically states that any model can be learned using almost any part of the brain. The hypothesis is empirically supported by the experiments performed on mammals, whose brains successfully adapted to passing sensory data from modalities they were not originally bound to. However, it turned out that trying to mimic the thought processes by reverse engineering of the brain is infeasible, albeit it did lead to advances in some other fields of research. Just to make an analogy, reverse engineering of a real-world process of birds flying was also shown to be a dead end for making advances for machine-driven flight. While the attention of engineers was focused on ornithopters, that is, machines in which flapping wings generated both lift and propulsion, no significant advances were made towards solving the problem. We started making progress only after recognizing that designing machines that emulated the beating of a bird's wings was infeasible for exploitable artificial flight. Finally, this resulted with the development of the Wright Flyer in the beginning of the 20th century. If reverse engineering of the human brain cannot be exploited for this goal, then what can we do to improve our understanding of intelligence? An alternative would be to start thinking about building machines capable of acting like human beings. Like a child following in its parents' footsteps, intelligent behavior is maybe something that can be learned from example, even without a thorough understanding of the underlying processes governing that behavior. But if a machine can act like a human being, does that mean that it is intelligent? Well, it might be. However, we have to bear in mind that mimicked behavior does not necessarily imply intelligence. At some point in time, we believed that if an average human being wasn't able to discern whether it was communicating with either another human being or a computer program, that this computer program would hold the rules that govern human intelligence. Unfortunately, we were mistaken. Namely, regardless of the approach used for modeling the thought process behind decision-making, working on machines that act like people was more or less abandoned because performing well in the imitation game did not help us in understanding human intelligence. That being said, many have tried to beat the benchmarks. Yet we have to bear in mind that the Turing test, just like the Voigt-Kampff test from the film Blade Runner, still remains unbeaten. Now let us shift towards the modern times and think about how AI is perceived today, by taking a look at several examples from popular science fiction films. The utility droids from the Star Wars franchise, for example. The one on the left is the jack-of-all-trades helper, whereas the one on the right is specialized in etiquette and is a universal translator. Are these types of intelligent agents available in the real world? Well, automatic translation between languages, both text and speech, is now considered mostly solved. However, we don't know yet how to make machines for automatic solving of non-specialized, that is, general-purpose problems. Terminator is a lethal autonomous weapon. We already have those, albeit not as sophisticated as the ones depicted in the films. However, standard procedure still requires that a human being is the one to pull the trigger, although this is not in any way imposed by the limitations of technology. A replicant from the film Blade Runner is a machine that acts and feels like a human being, up to the point of self-awareness, and is almost indistinguishable from one. Don't worry, we are not even remotely close to having this. Now, after reviewing the major schools of thought pondering on AI from different angles, we can describe an entirely different path. Noticeable advances in truly exploitable AI were reported only when the core focus of researchers shifted towards rational acting, disregarding the gist of all the previous approaches. But what does rational acting imply? Rationality implies optimality, evaluating decision-making and disregarding the underlying thought process. For example, if showers are probable in the afternoon, then the action "take an umbrella" is more rational than the alternative. In general, AI deals with the concept of creating machines thinking and acting like human beings in a rational sense. The purpose of these machines, often called intelligent agents, is to substitute humans in performing menial work, thus leaving us humans with more time to spend on more creative tasks, like dressing up your cat. We will try to formalize the definition of AI to some extent in the following slides. An agent, the cute guy over here, is a subject that perceives and acts. A rational agent chooses its actions so that it increases its expected utility, that is, its reward, which is shaped according to its purpose. For example, if we wanted to build a superb apple-picking robot, then its utility would be equivalent to its speed and accuracy at harvesting apples. For example, an appropriate utility function would be the number of neatly picked apples it can harvest in 1 hour. The choice of a rational action depends on the properties of perception, the environment, and the actions already taken. The abstraction of the real world implies that both the agent and the environment exist. We can steer the agent's actions, yet we cannot control the environment. Not directly, anyway. The process of perceiving, deciding on the next optimal action, taking the action, and waiting for the response from the environment is repeated in cycles. So, how does the process of deciding on an optimal action work? In order to understand this, we'll make a graphical illustration. Think of putting the agent in a maze with one or more exits, which we depict here as apples. The agent's goal is to navigate the maze and find an exit as quickly as possible. The time is frozen, which is the equivalent of one cycle of agent-environment interaction. The agent imagines the outcomes of possible sequences of actions and evaluates them. The one having the highest reward is designated the optimal one and is acted upon. The time shifts, the environment changes according to the actions of the agent and other factors as well, even pure chance, and the cycle repeats. You might be wondering, how is this simulated maze running computed? Imagine having an overview of the maze, where the expected utility of each and every possible state can be estimated. We can search the state space, that is, all possible policy outcomes, using algorithms for tree or graph traversal. We use an abstraction of the real world and approximation of future rewards to make finding a real-time solution to the problem feasible. This is the setup that enables us to navigate the maze efficiently. Sounds simple, right? Well, often the problem is more complex. Optimal behavior of the agent acting in a dynamic environment can be challenging due to several factors. First, there is the uncertainty of outcomes given the actions taken. For example, an agent navigating the ledge of a cliff might slip and fall into the abyss or a fire pit against its best wishes. Second, the overview of the present moment might be to some extent deformed or occluded because the agent's sensory input is often non-deterministic and incomplete. Just imagine having a perfect eyesight and having to navigate the ledge of a cliff while wearing this monstrosity. Your vision of the environment will be blurred, thus possibly inconsistent with the reality, which consequently might lead to choosing suboptimal actions. And of course, there is the problem of abstraction. Namely, it is hard to properly model all the intricacies of the real world. The dynamics of the system might pack severe penalties, even for some harmless-looking failures, like failing to grip a doorknob properly. And we haven't even started to discuss the possibility that the environment might be adversarial, that is, intelligent in its hostility towards our agent, for example, trying to push it over the ledge. Now, concerning abstracting the real world, when thinking about the state space size, for example, the size of the maze, we have to bear in mind that it might be infinitely large. In order to provide a way to deal with this overwhelming complexity, we introduce abstraction and specialization. You can think of an abstraction as a low-fidelity version of parts of the real world, which is less informative than the original. However, in turn, it is easier to handle. Try to think of a severely compressed low-resolution photograph of a scenery against the original high-resolution photo. Specialization, on the other hand, is a paradigm that enables the creation of useful abstractions, simple yet informative for solving the task at hand. Without it, we wouldn't be able to make the abstractions small enough. It also means that general-purpose R2D2-like robots are not something that we will be able to build in the near future. Next, let us consider the problem of learning by example in an abstracted domain, just to illustrate the concept. Imagine having to train an agent to distinguish between humans based on only the photos of their faces. Such an agent might come in handy for automated surveillance, for example, recognizing wanted criminals at an airport. The agent can be trained by presenting it with a large number of photos of faces tied to individual identities. In order to be successful, what the agent needs to do is build an abstraction model of the human face, such that will capture the most prominent features of each individual by encoding the original images, enabling it to discriminate between different faces. To make an analogy, think of a Picasso-style painting of a lady wearing a red hat. The painting is not entirely faithful to the original, however, in terms of representation, it might be informative enough. To broaden the definition, a learning problem can be defined as the problem of improving some measure of performance when executing some task through some type of training experience. The data we use is just a sample of a wider population, and we use different modeling techniques to find an appropriate way of abstractly representing a problem domain. Specific model architectures are then tuned to the given data, normally by minimizing an objective function, which describes how well the model fits the data. These models are then used to encode the real-world data in a way that enables them to perform well when presented with new data originating from the same population or domain. For example, if we train a model to discriminate between individuals, when presented with the photo of a distinct lady, the model should be able to recognize this as a photo of her and not of someone else. Trying to discriminate between types of objects in photos can be quite challenging. For example, if we wanted to build an agent that is capable of detecting cats in images, just consider the many different manifestations of a large variety of the Felis domestica species, involving also partial occlusion, within-class variability, elastic deformations, and background noise. The underlying complexity of this kind of modeling problem requires the use of highly expressive modeling techniques, such that can handle the specific types of variation in the data that is inherent to the problem domain. Thanks to the hard work of numerous scientists, recent advances in machine learning involving stacking representations and using enhanced model optimization techniques, gave us an end-to-end framework for dealing with highly nonlinear problems, otherwise normally requiring the use of feature extraction mechanisms. And if you're wondering if the concepts presented here in imaging data are transferable to data originating from alternate modalities, such as text or speech, the answer is yes. We will now take a look at several families of problems that we can, to some extent, successfully solve today. We can discriminate between thousands of different types of objects and photos of the real world, which was, for example, deemed unfeasible until 2012. We can perform real-time localization and classification of objects in a video. We can also perform semantic segmentation of a scene, which means assigning a class to each and every pixel in an image. Now, if the solutions to these problems do not seem very useful if considered individually, think of how they can be combined for automating specific, more complex tasks. One of these is autonomous driving. In order to properly navigate the state space, at each moment choosing the action having the highest expected utility, the sensory inputs, for example LiDAR, camera, and so on, have to be converted into meaningful representations. Accurate and timely object detection, localization and classification, as well as scene segmentation, are crucial building blocks for achieving level 5 autonomous vehicles, that is, those that require no human intervention for driving. At the present time, only level 3 automation is available for mass use. Due to the complexity of modeling specific conditions closely related to patients' characteristics, machine learning is increasingly becoming an essential factor in the implementation of personalized medicine in the clinic, for example, in the application of radiation oncology. On the illustration, we can observe an automatic robot for applying precision radiotherapy compensating for organ movement. Organ movement is modeled by combining low-intensity radiography and/or tracking visible markers attached to the patient. Autonomous unmanned air surveillance systems can be used for enhancing security in both remote, sparsely populated regions, for example for border control, illegal crossing, and so on, as well as for monitoring behavior of individuals in urban centers, for example crowd control at stadiums, during rides, and so on. Again, combining detection, localization, and classification gives us a powerful tool for implementing this. What else can we do using these technologies? Another exciting application is generating contextual free-form descriptions of images. This is commonly done using the already described solutions for inferring descriptive correspondences, that is, for localization and classification, as well as a recurrent neural network for building up descriptions conditional on the words that have been inferred. This is the natural language processing part. As you can probably guess, this technology can come in handy if you want to search over vast quantities of images. Just imagine browsing your messy personal photos or stock images from the internet using only natural language. But does this go both ways? Can we generate purely synthetic images from natural language? The answer is yes. The images presented on this slide were synthetically generated directly from their descriptions using a two-stage refining process utilizing stacked generative adversarial networks. In the first stage, low-resolution sketches are produced, while in the second stage, image fidelity is improved, giving lifelike high-resolution images. Next, many problems in machine vision involve translating an input image into a corresponding output image. As you can observe on the examples presented at the bottom half of the slide, inputting labeled sketches of a scene can be used for outputting lifelike images where specific objects are shaped conditioned on the labels, and vice versa. We can use this, for example, to synthesize realistic images from sketches, color historical photos, plot abstract maps from photos, and so on. Both image-to-image translation and video-to-video translation are commonly implemented, again, using the generative adversarial learning framework. This is a common technology that helps deal with a variety of problems, for example the problem of synthesizing a temporally coherent video, which assumes the need for modeling temporal dynamics. These solutions are capable of synthesizing high-resolution lifelike videos with altered content. This is also known under the name deepfake. You can observe some examples on the video in the top right corner. Basically, you can imitate any other person during a video conference meeting, given that enough videos of that target person is available to you prior to the meeting. And it does help if that person has the average look. Now, you might be wondering whether my look is real or am I impersonating Yul Brynner. On top of the several automation tasks that we discussed previously, we can also model intangible characteristics, like style, that is, mimic human abilities using artistic style transfer. Normally, art pieces are created by individuals that have mastered the skill to create unique experiences through composing a complex interplay between the content and style. We now have a way of automating this process of decomposing and recombining the content and style of arbitrary images, enabling the creation of novel masterpieces. This last example is my artistic contribution. If you're a fan of crime scene investigation shows, you might have noticed that in almost every episode there is a scene where they analyze a low-resolution image taken, for example, by a surveillance camera, and then somehow refine it to get an absurdly high-resolution image containing all the information they need to proceed with the investigation. Have you ever thought to yourself, well, this doesn't make much sense now, does it? Actually, it does. To some extent at least, as we will see in the following examples. We can restore damaged historic art pieces using a technique called image inpainting, which automatically fills in the damage, that is, missing details. We can also use semantic image inpainting to fix missing parts of face photos. This is done by finding the closest encoding of the available information of the corrupted image in the latent image manifold. Want to touch up your photos? Want to get rid of those wrinkles and look younger? You can do that now, even if you are not a Photoshop expert. But what about inferring plausible high-resolution images from low-resolution images? It can be done. However, we have to point out that plausible doesn't imply correct, because the details are synthesized from the training sample. Imagine being selected as a suspect for a crime from a low-resolution video surveillance image just because the features of your face are average for the population. We saw several examples of successful application of machine learning techniques for solving specific problems. Now we have to ask ourselves the following question. What is the driving force behind all the technologies we discussed previously? The answer is the data, vast amounts of quality labeled data. And how do we get this data? Prepare yourself for a plot twist. In order to make the computers do the boring jobs instead of us, we, human beings, have to do a lot of tiresome work first. There are many available sources of real-world generated data of arbitrary modalities, yet each and every instance of this data has to be manually labeled before it can be used for learning. This process of manual labeling is done by human workforce, often through marketable crowdsourcing services. If you would like to make a career in performing menial work requiring the use of human intelligence, you can do so. There exist farms where your job is to perform data labeling, like the one depicted here, which is in China. So, if you're an intelligent robot, you can lay back and relax a bit. Your time will come. Because the modeling goals are becoming more demanding, requiring the use of even more complex models, we need more and more quality labeled data to mitigate the variation. This holds especially for deep learning. Fortunately for us, both storage capacity and the processing power are becoming more accessible, that is, they are getting cheaper by units of measurement. This allows us to both permanently store almost infinite amounts of data, as well as tackle increasingly complex problems such that require more compute. After discussing several real-world machine learning applications, as well as the driving force behind it, let us shift our focus once again to playing games. Remember the apple-picking agent trying to navigate its way out of a maze? That's the one. Now imagine substituting the goal of efficient apple harvesting with winning a match in chess. In 1997, IBM's chess computer called Deep Blue has beaten the current Grandmaster Garry Kasparov in 3.5 out of 6 games of chess, thus asserting dominance over the former champion. The intelligence behind Deep Blue was driven by brute force tree search of the state space with a touch of alpha-beta pruning. Deep Blue was able to compute 100 million moves per second. Another exciting event. In 2011, a computer program has won the game of Jeopardy! In this game, the contestants are presented with general knowledge clues in the form of answers, based on which they must respond in the form of questions. Again, it was IBM that developed its question answering or question inferring system, built on NLP, information retrieval, knowledge representation, automated reasoning, as well as machine learning. We have to bear in mind, though, that the IBM's machine had an unfair advantage here because of its buzzer pressing speed. Go is a board game considerably more difficult to master than chess, using AI that is. Google DeepMind developed a computer program named Alphago that managed to beat the current world champion Lee Sedol in 4 out of 5 games in 2016. Alphago uses a combination of machine learning and tree search algorithms implemented through 2-phase extensive training. First, it learns to mimic human play by attempting to match the moves of expert players from recorded historical games, and then it is fine-tuned by playing against instances of itself, using reinforcement learning. If all of this seems fascinating, you should be even more impressed by AlphaZero, probably even terrified. AlphaZero starts with no inbuilt domain knowledge but the basic rules of the game. This means that no recorded historical games are used here. Instead, it quickly learns to play a set game proficiently only through self-play. In 2017, AlphaZero performance surpassed the current best world competitors, also programs, not only in the game of Go, but also in the game of chess and the game of shogi. The development of AlphaZero gave us just a small glance of the enormous potential behind fully self-learning techniques. The bleak future described in the Terminator narrative doesn't seem as unlikely now, does it? What about computer games? In 2018, a variant of reinforcement learning called Deep Q learning was successfully applied for learning control policies for several Atari arcade games, using only screen pixels and the game score as input. On the left you can see an example of the Atari Breakout game. The agent learns by trial and error, repeatedly choosing the actions that maximize the expected future rewards. Again, think of the apple harvesting robot, here having another objective. Dota 2 is a multiplayer online battle arena game. As you can see in the instantiation of a game in progress to the right, it is a vastly complex strategy game, meaning that the state space involved is overwhelmingly large for any given match. OpenAI 5 was the first to beat the world champions in this game in 2019, albeit on a somewhat simplified version of the game, which was achieved by imposing additional rules and limitations on the game in order to narrow down the state space. Regardless, this was a major milestone in game playing. Up to this moment, we presented several fun and useful applications of AI. Some of those are even superior to human performance. So, can we say that the age of human beings is at an end and that now is the time for AI to take over? Before giving a final opinion on this, we will first show some scenarios where AI fails miserably. What happens if we add a malevolent agent to some of the machine learning solutions presented earlier? Can we hack the models? Actually, we can. For example, intelligent face recognition algorithms can be easily fooled into misclassification, even when using a limited number of classes, using an eyeglass frame having affixed a customized color sticker, each sticker being tailored to the specific faces. Standard architecture road sign classifiers can be also fooled using visual adversarial perturbations. For example, a stop sign having additional graffiti on it might be mistaken for a speed limit sign. Encountering such a sign might end up bad for you if you rode a level 5 autonomous vehicle susceptible to such attack. Next, we can see that image classifiers can err in some cases even if only one pixel in the image is modified. A bassinet can be mistaken for a paper towel, and a teapot for a joystick, just to name a few. Similar examples led to the birth of many internet memes, such as this one. So what is missing? Why can AI models be so easily hacked? The answer is lack of context. Context being the one thing we still don't know how to encode efficiently. So, although AI technologies can be utilized for building autonomous agents that are capable of performing well in numerous tasks, even surpassing human experts in some, there are some limitations to this technology that makes the agents not so smart. First, the rationality of individual intelligent agents is strictly limited to the task at hand, which means that a face recognition agent cannot be used to play chess. Second, they can often be easily fooled into suboptimal acting, as we've seen in the previous examples. Human beings, on the other hand, can play chess and recognize faces simultaneously, even when people wear colored eyeglass frames. An intelligent agent most suited for a specific task can be compared to a human being having the seventh syndrome, at best. Moreover, whereas rational agents perform well on smaller scale problems in a simulated environment, for example chess, arcade games, and so on, the same cannot be stated for large scale problems. The real world involves uncertainty in a dynamic, ever-changing and highly complex environment. Here, an agent's performance largely depends on its ability to adapt quickly and from fewer experienced trial and error scenarios. So, if we want to make a transition from the simulated realm and be able to create utilizable rational agents in the real world as well, we need to find an efficient means of transferring the experience accumulated in the simulated environment to the real world, with cameras, gears and actuators. Without this, there is only so much that can be done on this scale. Finally, if you are thinking, will some intelligent machines take our place in the near future, you need not worry. They will not. If a specific societal or natural disaster wipes out a civilization or even the entire humankind, the robots will most likely not flourish. Thank you for your attention.